Welcome back. In the previous lectures, in the last module, we tried to understand the different interaction forces and also saw how these forces become significant for a very thin film. And we talked about the concept of Hamarkar constant, and then gave some initial examples where we could correlate how the stability of a system or a thin film is dependent on a couple of things. One is the spreading coefficient and one is the Hamarkar constant. So, what we will do today, we will extend our concept in terms of the spontaneous instability or understanding the situation which leads to spontaneous instability in an ultra thin film. So, this is the next module that we are going to start, where we talk about the spontaneous instability and dewetting in a thin polymer film. Before that, let us try to find out what exactly we mean by a thin film. Of course, thin film we have yesterday understood that the easiest way to define, or we talk about essentially a supported thin film which is coated on a substrate, which is the easiest system to sort of identify. It can be sort of spin coated or dip coated, or there are other mechanisms also. One can drop cast such a thin film. There are various ways. So, we have identified something to be a thin film when we understand that the interfacial interaction is active or present. So, essentially we talked about the if we are talking about the van der Waals interaction, this interaction is present in the system. So, you can immediately see that higher is the value of H, this will eventually, this excess interfacial energy, or let us write the excess energy, excess free energy of the system will tend to 0. Now, couple of important keywords we are going to pick up in today's lecture, and one of them is the word of dewetting. Now, let us try to build our concept on what is dewetting. Dewetting is a phenomena which has sort of it can be observed in macroscopic world as well. It is not that you really have to go down to nanoscopic length scales to observe dewetting. So, we will first talk about bulk dewetting of a liquid drop, let us say, on a solid surface, and then eventually extend this idea in understanding the spontaneous instability of a ultra thin film. Okay. So, the bulk dewetting, of course, we have already talked about surfaces which have different levels of wettability. So, based on that, a surface can be distinguished as a fully wetted surface or partially wetted substrate So, this is what is a fully wetted surface. So, this is the surface or the substrate. If you dispense a liquid, it will spread completely. So, the equilibrium contact angle is eventually close to 0, and this may not be a thin film, this can be a thick layer of liquid also. This can be a thick layer of liquid also. Partially wetted substrate, of course, there are where a liquid drop makes a finite equilibrium contact angle. And we have also argued that based on if the liquid is water. So, this is the equilibrium contact angle over here, and we have argued that if the liquid is water, then depending on what is the magnitude of theta e, we may identify a surface which is hydrophilic or hydrophobic. So, the general idea is that for the liquid to be water, if theta e lies in this range, that is, it covers both these two classes. This is completely wetted as well as this configuration, the surface is regarded as a hydrophilic surface. In contrast, if theta is greater than 90 degree all the way as high as possible, it is a hydrophobic surface. Irrespective of that, if a surface is partially wetting, we will just repeat a concept that we already know. It is something like this, let us say, or even it does not matter if theta exceeds 90 degree. So, let us say this is the surface or the substrate as we often refer to, which has a surface tension gamma s. This is the liquid which has a surface tension gamma L, and of course, this is the interfacial tension liquid. So, based on this, we know that one can write a balance of the horizontal components of the interfacial tension, and this also we know to get the Young's equation. As gamma s is equal to gamma SL plus gamma L cos theta e. But in the previous lecture we had also defined the spreading coefficient. So, may not be a bad idea to quickly recap its expression. S21 where we just use the notation like this. The film material was regarded as 2 and the solid was the substrate was regarded 1. So, the notation we are using today is essentially SL, or it was identified as gamma S minus gamma L plus gamma SL, and based on whatever understanding we developed yesterday in terms of preferential weighting and spreading coefficient, you can immediately now understand that for a system like this where there is complete weighting, the spreading coefficient is greater than 0, it is positive. Okay. Because what happens is you have a high surface energy substrate on which a lower surface energy would spread completely. So, if you are taking water, let us say, which has a surface tension of 72 millijoules per meter square, the obvious thing is that if you take a surface which has higher surface energy, okay, then water will automatically spread entirely, and this will be manifested with a spreading coefficient. In contrast, if you have a surface or if you take a substrate for which the surface energy is lower than the liquid surface tension is higher than that, then of course, the liquid will not try to spread entirely, or it will try to form isolated droplets. We will revisit this problem while understanding dewetting, and this is actually the fundamental point from which the concept of dewetting comes in. So, in a system where you have a partially wettable drop, it is reasonable to understand or argue that the spreading coefficient is negative. Okay. But please realize that spreading coefficient is based on a hypothetical situation where irrespective of what surface energy of the liquid and the solid you have, you are able to create a continuous film. So, you can calculate a spreading coefficient for a system like this, but remember spreading coefficient is essentially defined for this type of a scenario, and from this to this. So, the transition from if you can create a continuous film down to a partially wetted drop with making a finite equilibrium contact angle, okay, depending on the sign of spreading coefficient, depending on the value of equilibrium contact angle, is nothing but the physics of dewetting, which we will talk about. So, coming back to the Young's equation, what this gives, that on a specific substrate or material, a liquid has a constant contact angle. Thus, if you dispense on, if you take a specific substrate, let us say S1, and you sort of define a, you take a definite volume of liquid L, and if there are no significant, if the volume of the drop is not large enough that there are significant body forces or gravity acting on it. And there are no additional pressure distribution then the geometry of the drop will be governed by the balance of surface and interfacial tensions. This we all know. What in simple terms it means that the shape of the drop, okay, maybe I will shift to the new page. So, so the shape of the drop governed by balance of surface and interfacial tension, and in absence of body forces, that is the gravity, the role of gravity can be neglected, and no additional pressure distribution or temperature gradient within the drop, this droplet shape will be part of a sphere, because for a given volume a sphere, the spherical geometry, we all know this, has the minimum surface energy, but it can't take a configuration like this, because it is sort of limited its geometry or its shape at the liquid interface is governed by the equilibrium contact angle. Okay. So, this much we understand, and depending on the nature of the wettability, nature of the liquid, this equilibrium contact angle can vary between any, I mean it can be acute, it can be obtuse, whatever it is. Now, so what it means that for a given volume of a liquid, once you dispense it and based on the balance of gamma s, gamma SL and gamma L, the equilibrium contact angle is fixed. So, for a definite volume, so if you now see from the top, you would see the droplet to be like this. So, this is the drop. This is what is known as the liquid solid two phase contact line. You also know this, because I think we have, if not directly or explicitly talked about these concepts in while discussing hydrophobicity, we all understand this. So, essentially where does this picture originate from? if you take a section of this drop along this plane, you get to this picture. Okay. We already have argued that it is a part of the sphere. So, you get a circular contact line. In many practical examples, of course, you see a contact line like this, non-circular contact line. This is attributed to dust particles or surface heterogeneities. Which result in something called localized, this is an important word, pinning of the contact line. So, as if at these locations this contact line is stuck up, there is some additional force which is holding the contact line. We will be talking about pinning a little bit, maybe. It is an important phenomena and to a large extent responsible for various unique properties that is observed in flow involving droplets. And one of the thing that we have already sort of introduced you to in our earlier modules is the concept of contact line hysteresis. So, you take a drop like this and gradually tilt the surface, and you see that as soon as you tilt the drop, it does not flow, though the reality is that if g is acting in this direction and you have an angle phi making with the horizontal, the reality is the moment you tilt a drop, there is now a net force of g sin phi on this drop, and the drop should, sorry, it is illegible. Drop should immediately move because there is a net driving force, but it does not happen, and we know the difference in the magnitude between the advancing and the receding contact angle is actually a critical parameter in defining or determining or identifying the nature of a surface. For example, if you have a want to fabricate a super hydrophobic surface, not only your equilibrium contact angle has to exceed 150 degree, but you must have a very low contact angle hysteresis, which is typically of the order of less than 10 degree. A super hydrophobic surface, particularly if you are looking for application like self cleaning application, this contact angle hysteresis becomes a very critical parameter. But important thing to realize is that what is responsible for this contact angle hysteresis, and the scientific reason that is given or the argument that is given, it is actually the spinning which is responsible for the contact angle hysteresis, or in other words, the contact line at the advancing side of the meniscus over here is as if this is pinned. Okay. So, there are some additional interaction that arises which may not be always because of dust or heterogeneities, but there can be some localized interaction, localized additional enhanced forces, interaction forces, because what one has to understand that if one is looking at a geometry like this, the interaction, the interfacial interaction, let us say over here, and this is a macroscopic drop. So, this is a macroscopic drop, nothing like 10 nanometer, 20 nanometer, nothing like that. But eventually close to the contact line, it sort of asymptotically. So, this is the liquid interface, this is the solid, and though here the separation distance is much higher, it can be few hundreds of microns or maybe couple of millimeters. What happens is over the close to the contact line, actually these two interfaces come very close to each other before they actually merge. There is of course a theory, some people sort of grossly visualize a contact line to be a discrete entity where it just comes and merges at a fixed point, but there is a view which was first proposed by Nobel laureate Dijon, and there are many people who sort of subscribe to this view, is that well, the contact line is not a zero thickness zero thickness entity. At the point of contact it sort of stretches, forming a very thin adsorbed layer ahead of the liquid meniscus, and which sort of merge with the substrate only at an infinite separation distance. So, what happens is over this part of the film, you are now back to the regime of a thin film. So, ultra thin film. So, this is very thin. There are some experimental procedures based on which these type of films can be, the thickness of these adsorbed layer has been measured. Optical interferometry using an optical microscope platform is one such approach. And then you have so what happens is, as compared to the remaining part of the drop where there is no interfacial interaction, all you look at the, or if you take a bulk view like this, you are only interested in taking the balance of the surface tension forces, but close to the contact line you now have a regime where there is interfacial interaction. So, these type of interactions might be responsible for imparting these additional forces, but and resulting in pinning. So, we will not elaborate our discussion on pinning any further, because that is not the intention of this module, but it is important to note that pinning does exist. And also for our way of understanding dewetting and as well as spontaneous instability and how the dynamics is governed, we will take a picture of the contact line like this. Okay. So, coming back to this particular figure, what we understand that for a given liquid solid set, for a given substrate, given liquid and a given drop volume or a specific drop volume, since theta e is fixed. So, drop volume, theta e is fixed. Therefore, the drop, if you look from the top, occupies a definite area, let us say A1. Now, so this is the same picture. So, this we are looking at the elevation and this is at the plan. Now, if we do, so if we now take a drop which is making an equilibrium contact angle with the solid surface and then somehow perturb or disturb this block, which can be like you try to artificially spread it. Okay. And this is something you can do, it is a very simple experiment. What you can do is you can pour some water on a smooth table in front of you and then you just try to wipe it with your hand. Okay. So, that is very simple. I mean, I typically when I take a class, I just splash some water on the board and just spread it with your hand. And this is something you, I am sure all of you have seen. So, if you spread it, what you see that a spreaded drop, the contact line somehow retracts back and at certain locations. This is what is dewetting, nothing else. So, it is exact opposite of spreading, and this is what is known as dewetting. Of course, if you do an experiment like this on your study table or your dining table, in most cases you will see a contact line like this, it will not be circular. So, now you understand why it is not circular. Ideally, the contact line should have been a part of the circle, but due to heterogeneities present on the table or on the substrate, you will see a non-circular contact line. But even if you spread it with your hand, you will find that at certain locations it might be retracting back. Now, that is what is macroscopic dewetting. So, let us see what the phenomena occurs. So, you have this drop which is making this equilibrium contact angle, and by way of spreading you have actually made it like this. Okay. I am assuming that you have perturbed it in a fashion so that it still retains its symmetry. So, let us say this is now the new projected geometry of the contact line of the spreaded out drop. This was, let us say, occupying an area of A1, the initial area was A1. Now, after spreading, let us say it is occupying an area of A2, and it is making a intrinsic contact angle of theta I. So, if you now again write the Young's equation, what you will find, the left hand side remains the same, gamma s. The right hand side now is cos theta I. So, this is the total component of interfacial energy, vertical component of interfacial energy corresponding to the sorry, not vertical, the horizontal component corresponding to the intrinsic shape of the drop. And as we know that cos theta increases with the lowering of value of theta. So, since theta I is lower than theta E, therefore, this side is now higher as compared to the this side. So, the left hand side is now smaller than the right hand side, which means that there is an imbalance in the surface tension, and this imbalance also gets manifested with the fact that earlier the amount of area that was covered by the liquid was A1. So, the total surface energy of this part was gamma SL into A1, because this A1 is the part of area which was below the drop. So, therefore, the total surface energy was gamma SL into A1, and now by way of spreading, this liquid actually covers an area now of A2. So, the total area, that is, so the energy that corresponds to this is gamma SL into A2. So, this is that additional energy penalty. This is the additional energy penalty the drop has to sort of is occupying because of getting spreaded, and which also is manifested in this imbalance. So, what is the consequence? This additional energy has to be released, and that release is through the retraction of the contact line. So, what will happen? This contact line will start retracting towards the center, and as it retracts, what happens is the theta I progressively increases. So, if this was theta I 1 at an intermediate stage this will be theta I2, and as the intrinsic contact angle increases, therefore, what happens is this imbalance progressively starts reducing, and when the retracting contact angle that theta I sort of matches the equilibrium contact angle, the dynamics of the retraction stops, because then these two sides become equal and concurrently A2 also becomes equal to A1. So, there is no further energy penalty as well as no imbalance in horizontal component of surface and interfacial tensions. So, this is like an iterative solution procedure, you can say. Many of you are well conversant with programming and numerical solution of, let us say, nonlinear equation, where you sort of go on iterating, and when your solution matches the convergence criteria, your software program stops. This is something we all know how it operates and we routinely do it. So, exactly the same way this intrinsic contact angle, when it retracts and sort of this progressively goes on reducing with theta I gradually increasing, when it matches theta E, the dynamics controls, dynamics stops, and it so what is the whole sequence we talked? We had taken a drop which was making equilibrium contact angle. So, you dispense a drop on a surface and it will automatically take the shape of a perfect sphere if the effect of gravitational field, if the effect of body forces is negligible, and if there are no other additional temperature or pressure gradient within the field itself, okay, within the drop itself. So, then what we have done as a thought experiment or as a real experiment is we perturbed this drop which was making an equilibrium contact angle theta E to an intrinsic contact angle, let us say theta I1. This resulted in an imbalance in the horizontal components of surface and interfacial tension in Young's equation, as well as the drop is now or was now occupying more area on the surface, on the solid surface, which it is than what it is supposed to occupy based on its dispensed volume and the balance of its surface and interfacial tensions. So, this excess area that was getting covered corresponded to this much amount of energy penalty, which was also sort of a different way of representing it is the imbalance in the right hand side of the Young's equation, which was now higher. So, this led to the motion of the contact line towards the center, and as the contact line started to retract, the intrinsic contact angle sort of started to increase. So, as theta I started to increase, this cos theta I started to reduce. So, the imbalance between the right hand side and the left hand side started to reduce, and when theta I sort of matched with theta E, the retraction stopped completely. So, this is what is the phenomena of macroscopic dewetting. We all sort of have seen it, or if you have not seen it, I would suggest that you pour some small amount of water on your on a surface, on a table or on a glass plate or wherever you want to do, and just spread it with your hand a little bit. Of course, you will firstly, if you dispense a lot of water, you won't see a spherical droplet forming, you will see a rather flattish film. It is because of the fact that we now understand that if the drop volume is high, then you cannot neglect the body forces. So, the gravitation, due to the presence of gravity, you will have some flattening, it will not be part of a sphere. But even with this, so you now must understand, or you are now in a position to understand that why if you take a very small drop, you will see it is a part of a sphere, but if you take a large amount of drop, it is not part of a sphere, it is something like this, it gets distorted. Okay. And then if you spread it with your hand, you will see that at certain locations the contact line retracts back and takes close to this original morphology. So, this is what is dewetting, but what is interesting to note that here also you have observed a flow, because typically the way we study fluid dynamics or something like that, we know that a flow is typically triggered by either a difference in the height, which is the gravity driven flow, or like flow over an inclined plane, or you use a pump or a blower or something to force the liquid. So, you add a lot of centripetal force which gets which sort of leads to the flow, or you have a situation like a Coutte flow where one plate is moving and the liquid layer adjacent to the plate because of the no slip boundary, no slip condition sort of moves. But here is, you can see it is a unique situation where the flow has been triggered entirely due to the surface forces. Okay. So, this is also an interesting type class of a flow problem, and there is a whole branch of microfluidics which goes by the name digital microfluidics, which essentially talks about the flow of a droplet, and there are additional handling tools to trigger or actuate, stop the flow of a drop. So, this is in a nutshell the basic concept of dewetting. I would say this is the macroscopic dewetting of a drop, which involves which can be observed on a surface. Of course, important to note is that this type of dewetting you see varies largely on the wettability of the surface. In other words, if you have a situation where you have complete wettability, you will not see dewetting, because by way of spreading what you are doing, you cannot increase or reduce the equilibrium contact angle or the intrinsic contact angle. If your equilibrium contact angle is already close to 0, by spreading you are just allowing the liquid to spread more and occupy more area, and that is all, nothing more you can do. But in practical setting there can be additional effects. For example, when we talked about this spreading of a film or the dynamics of a liquid, we have neglected one specific factor which is always present if you are talking about real settings, that we have in none of our derivations or wherever we have completely neglected evaporation. Okay. In fact, there can be whole lot of experiments with a partially as well as completely evaporating surface where evaporation plays a very critical role, and I will not go into the details, but even if you have a partially wettable surface and you just leave it like that, you do nothing, you do not spread nothing at all, and you have evaporation, which is the case if you just dispense a drop of liquid even like water on a flat surface under ambient condition. If you dispense an organic solvent, the evaporation is much higher because of the lower vapor pressure, but even for something like liquid water, there will be progressive evaporation, and you might eventually see that with time the drop becomes smaller and smaller. Under ideal condition, the drop should always retain. So, what happens is the volume now shrinks, so or reduces because of evaporation. So, we argued here that the amount of area that a drop is supposed to cover depends on its volume as well as the combination of gamma s, gamma SL and gamma L. The combination of the surface tensions and the interfacial tension determines the equilibrium contact angle, but the exact area the drop is going to occupy is a function of the drop volume, okay? Assuming the density remaining constant, or in other words it is a function of the mass of the drop also. Now, what happens is, if you have evaporation, this contact line here also progressively you will find that the drop size is becoming smaller. Okay. So, if this was my initial location of the contact line, you might see that it has become like this after a while, and after a while it has become like this. So, this results due to progressive reduction of the volume of the liquid due to evaporation, and the dynamics, or how fast or slow this retraction occurs, depends on the rate of evaporation. Ideally, just like tilting of a drop on a solid surface, one would expect drop to start rolling immediately, but that does not happen, and there is a critical contact angle hysteresis only beyond this occurs. A similar thing can be observed in the dynamics, during the dynamics of this evaporating drop also. One would expect that the moment some part of the liquid evaporates, it would immediately sort of continuously move to its next location. So, the diameter will progressively get reduced, but many times what happens is, this is what is your equilibrium contact angle. Part of the drop has evaporated, but you still see that the contact line remains pinned to its original location. What does it mean? It means that now your theta I is less than theta E, but still you do not see any dynamics. And then all of a sudden you see that the drop suddenly moves by a large extent to its new location, making a contact angle like this. Okay. So, this where again it sort of the equilibrium contact angle matches with theta E. So, you see that this motion from the first to second to third pinned location is not a continuous motion. So, this is another very interesting class of problems which is also very well investigated upon. The motion is not continuous, rather motion is discrete, and which is this discreteness of the motion is again attributed to pinning effect, and this type of a discrete motion is often referred to as the stick slip motion. In this course probably I will not go to any greater detail with stick slip motion, but this is a very interesting class of motion. So, what you see that even after evaporation, though there is a, so this is your initial drop and there might be some evaporation. So, the volume increases, volume reduces. So, you are now in a shape like this where your theta I is now smaller than theta E. So, there is an imbalance now, okay, and this imbalance in the Young's equation, again in the right hand side there is an imbalance. So, it should retract, but it does not retract instantaneously and it sort of waits. So, unlike this rolling of a droplet or sliding or movement of a droplet on a macroscope on a tilted surface, it depends on the difference of theta A and theta R. Here there is a difference, critical difference between theta A and theta I, after which the drop starts to move, and then it moves to a location where again it sort of goes back to an intrinsic shape corresponding to theta E, and then again as if the contact line remains spinned over. There till again this dynamics occurs. So, this type of a motion is again attributed to what is known as pinning, and this type of motion is called the stick slip motion. So, both this as well as the example we talked where we take a drop initially making an equilibrium contact angle with the surface and then we perturb it by way of forcing it to spread and see the dynamics. This is both are sort of flow which are triggered by the surface effects or the imbalance in the horizontal component of surface tension, and these are examples of dewetting which we will talk in which we have sort of introduced you to. Important thing to note here for a setting like this, that the flow is engendered by imbalance in surface tension, the horizontal component. So, this is what is bulk dewetting, and based on this we will now start talking about the dewetting in an ultra thin film, and we will be talking about the dewetting in a polymer thin film in a liquid form, but this phenomena is possible in any ultra thin liquid film. Of course, we will argue why research is more oriented towards polymer thin films and not with other types of thin films of simple liquids like water or any organic solvent. Thank you.